Okay, so as Enrico already alluded, I'm going to basically complete the first part where, which was mostly about the computation of the integrand, and I'm going to tell you how we actually dealt with the integrals. And as Enrico also said, there's two parts to this. There's on the one hand what he called the virtual part, and there's the real part, which includes phase-space integrals. And I'm mostly going to focus on the phase-space integrals because that's really something that was not so much covered in different talks. And for the virtual integrals, I'm going to point you to the talks by Rodolfo, Carlo, Ludovic, and Mao, where especially Mao spent a lot of time explaining how to do these integrals. So maybe we can first take a bit of a step back and look at an expression which already appeared in the original paper by KMOC. And that's here, for example, the impulse kernel at next to leading order. And if you look at it, you see that there are many different terms in this integral that you have to perform. And in particular, you see that there are tensor integrals, there are delta functions, there are even some derivatives of delta functions, which come from expansions of the arguments of those delta functions. And the question then boils down to how to compute this type of integrals. And in principle, we would like to build on the method we explained for basically doing the computation in a soft. Which we did in 2020 together with Mao and Julio. And in principle, it's very straightforward to generalize what we did there to also treat cut integrals. And one just needs to import a simple insight from particle physics. And that is that if you do IBP, the IBP relations themselves, they do not depend on the I epsilon. You have, of course, to be a bit careful with using symmetries, but in principle, you can track the I epsilons, and so you can also do IBPs with different I epsilons. And then what you can realize is that you can express those delta functions that appear in terms of differences between propagators with different I epsilons. And this is something that is very well known in collider physics, and there it goes by the name of reverse unitarity, which originally was used by Anastasi and Melnikov. Okay. Once we have this reverse unitarity at hand, we can proceed in the same way as we did for the virtual integrals. We can do soft expansion and IBP reduction to master integrals. In fact, we can even use the same integrand that we had and just impose the cuts on it. And in the end, we have to compute these master integrals that we get out. And for this, we will use the method of differential equations, which was explained in some details by Mao's talk, but Mao focused mostly on the virtual integrals. The key point here is because the IBPs were independent of the I epsilon prescription, the differential equation will also be the same for these integrals, because a differential equation essentially only depends on IBP reduction. And this means in particular that we know everything for this type of integrals. We know the canonical form, and this was also presented already in our first paper on this topic. Some small point is that we can drop some masters, and the symmetry of the problem is typically reduced once you impose cuts. And so in principle, we can recycle this differential equation that we computed first for the potential region, but we essentially gave all the relations also for the soft region for different problems. We can pose cuts, and we can also specify two different regions. The only thing that in all cases is non-trivial is computing the boundary conditions, and that's what I will spend now some time on. Some comment we will stay in a soft region here. So how do we do the boundary conditions? So the first type of integrals is two particle cuts. Those are essentially trivial for us, and they there's also something that was in Ludovic's talk. Basically, once you have a two-particle cut, it reduces to some transverse convolutions between some left-hand side and some right-hand side. And the soft expansion essentially trivializes the integrand insertions on the left and the right of the cut, because it can be fixed simply by dimensional analysis. So you get some closed form expression relating this cut integral to basically the integrand evaluated at a fixed value of momentum transfer. And this works to any loop order, so the two particle cuts can, for all intents and purposes, really considered to be worked out to all orders. Then we have to compute also three particle cuts starting from the two loop order. And for these, we have two sources of boundary data. On the one hand, we are using cutting rules, which I will explain a bit more later. And the cutting rules together with the virtual integrals, which we assume that we have to compute anyway for this kind of observables. And what we also do is we use the velocity expansion, similar to what Ludovic was talking, but we do it in a way such that we do it in the method of expansion by regions, and we add up all the regions to recover the soft value in the boundary in the neostatic limit. And for a very in-depth discussion of these regions, I refer you to Mao's talk, where I think he very nicely explained the different regions in the problem. So these two sources give us an overcomplete set of constraints. And we can just pick the simplest ones to fix our integration constants. So what we did is we used unitarity for the H-type integrals. So H-type is everything that only has two meta lines for us. And for those, we only have a single S-channel cut. So the three-particle cut of this integral will be exactly related to the imaginary part. And this virtual integral we have to compute anyway. So, and the second way we can compute the boundary conditions is actually the neostatic limit. And here we separate our space, our soft space into different regions. And so in principle, there's the potential, the radiation, and also the genuine soft region, which we also sometimes call the quantum soft region. And then we can see how all these regions scale in the neostatic limit. And you will find that the potential region, the region where all the gravitons are in the potential region, is a dominating region. But the three-particle cut doesn't have any support on this because the central graviton has to be on shell. So this means the next to leading contribution actually comes from the potential times radiation. So the central graviton is radiation, and the two gravitons on the side are in the potential region. And then you can do a very simple power counting argument to see that this scales basically as velocity to the -1. And once you combine it with the prefactor for the pure integral, you'll see that the integral, the pure integral, actually vanishes in the static limit. And these two rules together allow us to fix all the boundary conditions for the cut integrals. And it's, I think, very nice that in principle one only needs this power counting arguments and unitarity. And for the three particle cuts, we don't need to do any new computation, so to say. Let me quickly spend some time on what I mean by cutting rules. So I think it's a very well-known fact that the sum over all cuts in any given diagram vanishes. So for example, we can look at the S-channel cuts for some double box diagram, and we can see that all the contributions from all the S-channel cuts has to sum to 0. And there's some you have to keep track of I epsilons, but that's something that is very well understood in the literature. And then if you collect these integrals, also use some symmetries, because some of those cuts are actually related, you can find very nice relations that should be satisfied by those integrals. For example, the imaginary part of this crossbox integral is related to the three particle cut plus the imaginary part of the two particle cut. Same for the double box, and for the H diagram, you have this relation which was already on the previous slide, and the prefactors here are due to the multiplicity of the different cuts. So sometimes a cut will appear twice, and sometimes it only appears once. So far this discussion was for quadratic propagators and with scalar insertion, but it very easily also generalized to eikonal propagators, so this is linear propagators, and to tensor insertions. The only thing you might need to keep track of is that the symmetries are typically broken by tensor insertions. And as Enrico already said, we can use these relations already at the abstract level. They should in some way also hold for the amplitudes, and this allows for this simplifications which we described in our paper, and which also shows some relation to the eikonal, for example, with this tree cube subtraction that we saw on one of Enrico's slides. Okay, yeah, I think then I already tell you something about the results. So as Enrico was saying, there's two quantities that we are interested at this level. On the one hand, there's the angle, including radiation, and the radiated energy. At higher loop orders, there might in principle be more angles and more energies. But at this order, this is a set of observables. And the radiated energy is basically known by Damour and also by Di Vecchia, Heisenberg, Russo, and Veneziano. And therefore, I'll spend some time talking about the radiated energy. And the radiated energy is actually it's actually very simple to do. The integrand you just get by gluing together two 5-point amplitudes. That's also similar to what Di Vecchia and others are doing, and what we also saw in other talks. And then you can compute this basically with the techniques I was explaining you. And it's very simple in this case. You only have to compute 6 integrals, and this is what we did in the first paper, in a short paper. If you want to get the full impulse, this is a bit more complicated. You actually have to compute the virtual integrals. There's a total of 22 virtual integrals. Of course, as we heard, the number of actual integrals might be reduced by a bit if you focus on the relevant contributions. Once you compute then this observable, and you insert all the values of the master integrals, you get a quite compact formula for the radiative impulse, where you find the well-known arcsinge function and also some new logarithm function, and it's all expressed in terms of quite a few functions. Yeah, something that we already heard is that the radiated energy at this order is purely longitudinal, and it can be written in terms of a single function of the relativistic factor. There's a new function which appears only in the radiative sector, and only also in the radiative energy. So yeah, and the very interesting thing now to do with this result for the radiative energy, this was all in the scattering regime, is of course to do the analytic continuation. And fortunately, this was already described by Bini, Damour, and Geralico, and also all this story about analytic continuation also has close ties to what Kellin and Porto talk about. So there's a very simple formula relating the elliptic radiated energy to the hyperbolic radiated energy, and this is then what is basically the final result. And essentially, the function that you get here is just twice the function that you get in the elliptic case. And the analytic continuation of the function is also very simple. So this arcsinge is an arc-cosh in principle. So and it continues to an arc cos with some I, which cancels with the I coming from the square root. Okay. With the result at hand, we can do some studies. The first thing we, of course, looked at is that the high energy logarithmic divergence cancels. We also computed the very same thing in n equals 8 supergravity. And we find, relating to some earlier studies of universality in this classical models, that the radiation is actually not universal. And yeah, I think that's something that might be understood from the fact that the messengers are different in n equals 8. So you don't only have the graviton, but you also have vectors and so on, which can propagate. The structure of the high energy limit agrees with some old results, although the numerical coefficient doesn't agree. But it was later verified by Damour, I think, and by others, that the numerical coefficient in the high energy limit is actually, so our result is actually correct. We can use our result and do a PN expansion, which is natural to get in contact with the literature. And what we find is that once we expand, that we agree with the literature, and also apparently with some unpublished result by Bini, Damour, and Garalico, which Thibaut Damour informed us that they computed basically up to the v to the 15 and agree with the closed form expression that we give. And also there is some recent result which we also heard about earlier in basically it's PM, but they have to expand their result in order to compare with us, and they agree at least up to order v to the 7. But in principle, I think this can be performed to any order. Okay. We did many more checks on our results. So first of all, the scattering angle was known before, and it agrees with a result by Damour. The radiative energy was later verified by Di Vecchia, Heisenberg, Russo, and Veneziano. PN expansion, as I said, also agrees with the literature. Something that is also quite interesting and non-trivial. So the radiated energy matches the IR pole of the conservative contribution at 4 p.m., which basically was published at the same time. And yeah, it's a highly non-trivial agreement. Also, something that I think it came up in some earlier talks, was that we also recompute the fully conservative result. So in principle, there's nothing that stops you to restrict the KMOC setup to any given region. And we restricted to the conservative setup, and we recomputed basically the conservative scattering angle. Of course, once you have the full radiative result, that's maybe not so much of a check. The integrals themselves were very strongly checked. We performed numerics in all different regions, in Euclidean and scattering kinematics. The cutting rules, as I said, it's kind of an overcomplete set of relations, so we could check those. And the integrals were also independently computed by Di Vecchia, Heisenberg, Russo, and Veneziano. And maybe something just to give you to take home is that in our last paper we actually give a full set of all mass integrals that you would need for this KMOC computation at this order. So in principle, anyone who is interested in doing this kind of computing an observable in this kind of approach can just pick up our result and compute for their favorite model. Let me finish up by talking a bit about what we would like to do maybe in the future, and which also came up in other talks. So I think the most interesting relation to other approaches at the time is differential observables. So what we are quite efficient at is computing this fully inclusive observables because they have so few scales. And what we would like to do is basically to, instead of the radiated energy, we would like to go to more differential observables like the spectrum and angular distributions. And this is actually exactly the opposite way of what, for example, Gustav told us, and what we also heard in the other talk earlier today, is that we in a more traditional approach, you would start by the waveform and then adding integrations. And for them, actually, the last integration or performing more and more integrations gets hard. So it would be nice to somehow meet in the middle. And I think for example, the radiative energy spectrum is something that we is quite feasible for us to do. Something that would be very nice for the future is to treat the regions a bit more seriously. And so instead of using the soft region, to go to the potential region and radiation region, so to fully exclude this quantum region, which we would not expect to contribute. And this would already kill all diagrams, for example, the box bubble, which we would not think of as classic anyway. And we have a quite good understanding, I think, to change basically the boundary conditions from soft to a more restrictive region. Of course, radiation at the 3 p.m. order, 4 p.m. order is a very active topic, which maybe we could look into, because especially again the radiative energy might be something that is very simple, as it was at the 3 p.m. order. And finally, it would also be interesting to go a bit more in the direction of to study more general processes, for example, with massless external states, which was covered in the talk by Gonzo. And I think that's also something which should be doable at higher orders in G. Okay, yeah. So with that, let me also thank the organizers for giving me the opportunity to speak. And yeah, I think you can feel free to ask me, either me or Enrico, questions to either of the talks.
Okay, thanks, Michael and Enrico, for the great talks. And please raise your hand if you have a question or comment. Or just chime in. Yes, Thibaut.
Maybe I can ask. Oh, sorry. Please.
Sorry, you can speak first if you want.
Oh, maybe just a technical question. So I noticed that when you do the reverse unitarity, you have cut some double propagators. Mm-hmm. Can you say a bit more how you treat that in practice?
In practice, the cuts and double propagators, they are just derivatives of delta functions, right? So it's the same kind of relations. I mean, you can also, I mean, if you want, you can also perform IBP reduction before.
But the cuts you have, they're actually like the physical cut, including the positive energy zeta function.
Ah, okay, yeah. So I think we, so there's actually some positive energy theta function hidden always. So in principle, you can also write this relation, I think, with a theta function. I think then the I epsilon prescription is still it's still a bit different than I think. I think you can still write it as some difference of propagators, right? I mean, in any case, you could also add the theta function and then keep it always, and then just care about it in the. I mean, the only point where you really need is for the computation of the boundary conditions, right? And for the boundary conditions, this actually we use unitarity again, right? So there is a theta function, and for these other arguments, since it's 0, the theta function this only depends on the scaling, and the scaling is independent of the theta function. Okay.
Okay, the question I wanted to ask, which is a bit trivial, but just to understand. So you say the computation of the radiated energy is easy for you. Now, nobody succeeded in computing it starting from the phase space integral you were showing from the h mu nu square phi k0. So is it reverse unitarity, which deconstructs the phase space integral, which is the main thing, or you need, it's more than that? You need these differential equations? Or...
It's probably the reverse unitarity which helps you the most, I think. I mean, of course, also the virtual integrals, they are probably also hard if you don't use the differential equation. So it's probably a combination of both, yeah.
Okay.
Maybe just to comment that since Michael said we gave all of the integrals, including the cut integrals. So in principle, the people who compute the classical waveform first, they could just transform it to momentum space, IVP reduce, and using reverse unitarity and use our integrals. So there should be the same integrals that are appearing in that case. But it's easier to do it before doing all of the integrals of the waveform. So one would have to reorganize them in terms of diagrams like we have.
Okay, thank you.
Any other questions or comments?
Maybe just a comment. So there's been some discussion about I epsilons and how at high orders these are subtle and why one has to worry about them, especially at the next order. In principle, KMOC takes care of all of that because it's directly computing the like real-time evolution observable. So the amplitudes methods clearly can be applied to that too if one computes within KMOC. Okay, no one has tried that yet, but in principle, the formalism is set up in a way that the I epsilon shouldn't be a problem, and we can use Feynman I epsilon plus cuts to compute these observables, just like at two loops. I know some people are worried about that, but the computation can be done fully in terms of Feynman I epsilons and cuts.
Are you saying, sorry, also that you can take the informalism and take the, let's say, the prescription for the external X and put them on share, and that's equivalent to the KMOC. So that's what I think at least.
Yeah, that's what I'm saying. That it's just an in calculation, and you can do it with retarded propagators and advanced propagators, or you can do it with time order, anti-time order plus delta functions, and KMOC makes the second choice. Which is useful for us because we know how to compute the integrals.
So, Michael, on your last slide, you talked about
first, I guess.
Yes, observables with massless external states. You mean essentially the waveform?
For example, yeah.
Okay.
I mean, I was just referring to Ricardo's talk, which yeah.
And what does the post-Newtonian expansion have to do with just above there, the Jakobson?
It's the point being that those are only available in post-Newtonian expansion, right? Those differential observables. Yeah.
So far.
so far.
Well, as
Yeah, maybe one comment for these more exclusive observables. It's like, I mean, if you think back in collider physics, by now, like people at n cube LO in collider physics, like now even rapidity distributions for the Higgs are known. So these are also like more exclusive observables in the Higgs case. So, and that's like at 3-loop order. So like in terms of complexity, it seems completely in reach to do that in the gravitational setting. So just to give you a like feeling of scaling and what has been achieved in the context of collider physics. So this is not like the end of the road. Like, I mean, I think there is still a lot of progress ahead for the gravitational setting. So just to give us like some optimistic outlook of what can be done.
Yeah, it's also interesting because there was some discussion, right, about that the functions may be much more complicated, but for us it's probably again still very simple. I mean, it will again most likely be just some known functions from collider physics, right? Probably.
Yeah, my guess would be that will be like you have additional variable like omega times b, and yeah, it's of order v, but if you want to do that in order in velocity, then you have to do some in this expansion.
Yeah, it's a 2-variable problem. And the natural variable is b omega over v. I think that's the second one. Yeah.
Mm-hmm.
Yeah.
It would be interesting to see what kind of functions shows up.
May I make a comment on terminology?
Yes.
This inclusive versus exclusive. I think in particle physics, we use exclusive and inclusive. You know, it's due to Feynman, actually, remember this distinction, in a slightly different sense, in the sense that, for instance, you have, say, proton-proton collisions. An exclusive cross-section will be one in which you observe, say, a certain final state with a given number of particles. And inclusive will be, for instance, a single particle distribution in which you say, I have proton-proton, and I don't know, I look at the one proton plus anything else in the final state. Now, it looks to me that when we are talking about gravity, we are really not talking about an exclusive process. We are not really talking about our two massive particles giving two massless particles and a single graviton. That's what we compute, but the real meaning is inclusive in the sense that we look at the total energy carried out by many gravitons. Do you agree with that? I mean, somehow this has to do with the fact that what we produce is a full coherent state of many, many gravitons. Each of
I mean, you're right in the sense that.
Yeah, please go ahead.
Sorry. I mean, you're right in the second term in this KOMC framework, right? We're summing inclusively over everything up to a given order, inclusively over everything that can be exchanged. Yeah, maybe we should call it more like, we call it like, I mean, this differential, let's call them more differential or more like event shape type observables.
Yeah,
like
differential, I agree, of course, in the sense of the variables we look at. But in a sense, it is not exclusive in the old sense of particle physics, where you have a fixed number of final particles, a fixed number.
I mean, by inclusive versus exclusively meant over like what bins you're summing, like what energy bins or like what angular bins you're summing on the final state particles. But I mean,
it's whether you restrict the phase space or not. You can restrict to one particle, two particle, three particle, or to like certain directions. So we just use it in a very general form where we say that something inclusive is when there is no restriction on the phase space at all. And something more exclusive is when there is some.
That's exactly what I'm saying. In the old days, we are talking about a one particle inclusive cross section, which still depended on the momentum of the particle. You see, you want to know. And then when you say integrate over that remaining momentum, you actually compute the multiplicity times the cross section, not just the cross section. Now, if you weight with an energy factor, then indeed you compute the energy loss. But okay, it shocks me a little bit to use this same terminology, but now I understand in which precise sense you mean it. Yeah.
So just a comment that when you make any restriction on the phase space, there can appear large logarithms, which they're not, I mean, this inclusive versus exclusive sometimes is used also to talk about whether there's infrared divergence or not. But there's other problems with any cuts on the phase space, which you can get large log.
You are absolutely right. And this is precisely the point. I mean, if you were looking at an exclusive process in the sense that you fix the number of final quanta, you typically run into infrared problems. And so I think implicitly what I think it's quite clear also in CMOC that, you have your S matrix, right? And you sandwich your observable between the two S matrices, but those S matrices, they are, they are forming a coherent state of particles. They have operators like Paolo was explaining yesterday, Bloch-Nozick-like operators. So then your observable acts on a coherent state and just reads what sits there in the exponent. And in the sense, then you forget about the coherent state. But,
yeah. Also, what happens with this quantity in particular, right, is that you're looking at the absolute value squared of the waveform.
Right.
But many of these effects, they result into an exponential phase, and then you might not need to worry about those. I think at some point we are going to look at observables which depend on the phase of the waveform, and any infrared subtleties then will become more important, and we'll have to learn how to deal with this. I think there was some preliminary exploration of this in this paper by Ricardo and Andre on event shapes for gravity. But I think kind of an understanding of infrared divergence on the phase of the waveform is something that will become important in the near future.
Absolutely, I agree. Yeah.